go. Okay, let's go ahead and get started here. Good morning from sunny Denver, Colorado, and Centennial, Colorado. This is our monthly webinar, and this month's topic is making repeatable measurements during route-based condition monitoring. We are going to talk about some ways to utilize MEscope to make your route-based monitoring easier and expedite things and make it more informative for you. Hopefully provide you some tips on how you can better utilize MEscope and console for doing route-based condition monitoring. With me, this is Mark Richardson, and joining me is my dad, Mark Richardson, as we like to call him, Senior. And we also have Brian Schwartz from Vibrant Technology is also joining us on the line here. A couple of housekeeping items during the webinar. If you have some questions, go ahead and type them in on the panel on the right-hand side. At the end of the webinar, we'll go ahead and unmute everybody. So if you do have some questions also, we can utilize audio. But we'll try and get all your questions answered before the end of the webinar. And if some things run long, we will be sure to respond to you via email as well. With that, I'll hand it over to my dad. Dad, if you want to go ahead and take the reins.
Thanks, Mark. Let me just add a little bit to what Mark said. You can see on the screen, I have a camera in my office here. It's right next to where I'm sitting at my desk, and you can see the infamous or maybe famous Jim Beam, which is one of the models that we have in MEscope that we use a lot for demonstration, and you can do impact testing on that. What you see there is an accelerometer just fastened to the top of the Jim Beam, and I'll just put my impact hammer up there on the Jim Beam so you can see that I can do either a roving impact test on this beam or a roving accelerometer test. And if this were a machine out in the field and I was doing troubleshooting with MEscope to look at its resonances, look at its ODS data, probably the easier way to do it would be to impact at a single point and rove an accelerometer around, especially if it's a triaxial accelerometer like this one. And you can see the analyzer behind. There's a 4-channel analyzer there that's plugged into my computer. And we're going to look at that in a minute and actually take some impact measurements on the Jim Beam. And so the title of our talk is Repeatability. This is something a little bit new that most people don't think about or even be concerned about when they're taking data on a structure with an impact hammer. So the question is, am I impacting at the same point all the time as I rove the accelerometer around and take data on the machine or the structure? Now, in the bottom of the picture is what Mark talked more about, and that is a rotor kit, and it's got some magnets on it. And so the second experiment we're going to do, and you can see the 4-channel analyzer that's attached to a triaxial accelerometer, and also the fourth channel is a laser tachometer. So we'll look at that experiment secondly, and I'll show you how repeatability can be used when we make measurements on a rotating piece of equipment like this. So how do we measure repeatability? That's really the first question that needs to be answered, and we're going to use something that's in MEscope, maybe a command that you haven't used very often, or maybe you don't understand it, and it's called SDI, or the Shape Difference Indicator. It's very much like the Modal Assurance Criterion, or the MAC, which is and both of these measures are correlation coefficients between two vectors of data. So if I have two mode shapes, if I have two ODSs, if I have two sets of time or frequency data, I can use these correlation coefficients to tell whether they're the same or different. Let me go back to one of our technical papers. I'm going to go out here to, this is MEscope running. I'm going to click on this link here, which will take me directly to the Vibrant website on the internet. And many of you may be familiar with this, but this is a good place to look at technical information that's available from Vibrant Technology. We have both tech papers and app notes and a few case studies out here too, and videos and so forth. So I'm going to go to technical papers and click on that menu item. Now here's a list of our technical papers that are available on the internet. They're categorized here. I prefer to go by number, so I'm going to go all the way down here to the bottom. You can see that there's quite a few, 68 different technical papers. These are papers that we have accumulated over the years. Some of them go back into the 80s and 90s, but we go to technical meetings on a regular basis and present some of our technology that's implemented in MEscope. I'm going to go to this paper here called Using Modal Parameters for Structural Health Monitoring. Let me click on that paper. This is a recent paper that we just gave back in February, and you can see there's our friend the Jim Beam again with a impact hammer and a triaxial accelerometer. Let me make this even a little larger. And this is where we use this SDI metric, or correlation coefficient. So the paper explains the difference between a MAC correlation coefficient. MAC values are always between 0 and 1. Now MAC is similar to coherence, and we'll look at coherence in a minute too. That's a different way of measuring the collinearity between an input signal and an output signal to a machine or structure. So those are typically things we measure in an FRF, frequency response function. We measure the force in, we measure the acceleration out. So think of it as the Jim Beam is a black box, and I'm going to put some force into it and measure its response to that force. That's a standard calculation that we use in modal analysis. So here's a little picture of how MAC measures the collinearity between two shapes. And again, a shape is just a vector with numbers in it. It can be complex, real and imaginary, magnitude and phase. It can be real with just plus and minus signs, anything like that. These metrics will work just fine on. But the MAC value measures, just like coherence, it measures the collinearity between two vectors of data. Now, coherence is in the frequency domain, typically as a function of frequency. MAC is used to compare two mode shapes or two ODSs. If they're collinear, the answer is 1. If they're different than one another, you can see here shape B is pointing off in a different direction than shape A. Then the MAC value starts to drop between 1 down to a value of 0. So here's a little bit of mathematics. And here's SDI. SDI is similar, but it can actually measure whether two vectors are in fact different from one another. So a little more accurate than just whether they're collinear, lying on the same line. If they lie on the same line and the shape A is a little bit shorter than shape B, then the SDI is going to pick up that difference and have a value less than 1. Let me show you another picture here just to make this a little clearer in case this is a new thing we're doing now. When we do these presentations at technical conferences, we are creating PDFs. So here's another link in the PDF of this technical paper. If you don't like reading all the words, here are the PowerPoint slides that we use to present this idea. So now here in this paper, what we were doing is actually storing modal frequencies, curve fitting some output only data. These are ODSFRFs. Well, in this case, it's a cross power spectrum, very similar to an ODSFRF. We can curve fit that data in MEscope and get a set of modal frequencies and damping. So we're using SDI here as a metric to tell when, in this case, whether the torque value of one of the cap screws on the gym beam. Anyway, that's a different talk. What I wanted to bring you to is this picture of a Mach plot. So here's a kind of a three-dimensional plot of the Mach values between a vector A and a vector B. Now, vector A has got components of 1 and 1. Vector B has got two variables, X and Y. So that's what's plotted here. Here's a plan view of it, and you can see that all along the line of vector A, the Mach value is always 1. If vector B gets off of that line, then the values drop down away from 1. So again, it's a correlation coefficient between two vectors. Here's a plot of SDI, a little bit different. You can see that it only has values of 1 at 2 points, where the vector A is equal to 1, 1, or when B is equal to 1, 1, or when B is equal to -1 and -1. This would be the negative of vector A. So a little bit different picture, but you can see that when vector B is anything different than 1, 1, the values of the SDI drop dramatically all over the plane of values here over which it's plotted. So let's go back now and see how we actually use this with some real data and make some measurements here. So I've got two projects here in MEscope. The first one is called Repeatable Impact. So let me bring that up. I'm going to open this project. And here's a 3D model of the gym beam, and these are all the points that would typically be measured on the gym beam. Now we're not going to go through a whole impact test here today, but the way we measured the modes of the gym beam, or a set of FRFs, was to impact at one point and rove a triaxial accelerometer to all these various points on the gym beam. So you can see that the orientation of the accelerometer is very important in order to do an animation from the resulting data. Let me go to my hotkeys here. This is a standard feature in MEscope now, where I've created 4 hotkeys. You can see one of them is, the first one here is impact the structure. The next one is check repeatability. The third one is update the baseline. So when we talk about making a repeatable measurement, repeatable with respect to what? The answer is that we've already got a baseline measurement, and in this case we want to make sure that when we do the roving accelerometer test that we impact at the same point always. So this is a very simple application of repeatability where I will save away a baseline, and then each time I take data I want to see whether my impact point is the same. In other words, is that baseline measurement being made exactly the same as the last time? So there I would, in order to make the baseline, I would just mount an accelerometer somewhere, anywhere on the structure, and that's my reference. And then when I impact the structure, I'm always measuring the same FRF between the impact point and the reference accelerometer. So that's what we're going to do here in a minute. Let me just show you some of the mode shapes of the Jim beam. You know, we've gone through curve fitting, and here they are over here in this shape table. We got frequency and damping of the various modes. The damping of these mode shapes is quite different. That's because the boundary conditions are different. It's sitting on a foam pad, and depending on the mode shape, each mode will absorb the damping from the foam pad and also the surrounding air in a different way. But as I click through here, you can see these mode shapes. Of course, this is a very easy structure to test, and the data is very easy to curve fit. But just attaching 3 plates together like this with some cap screws, you know, creates a much more interesting set of mode shapes than if I had just tested one of the plates by itself. So as soon as they're bolted together, we get all sorts of different shapes. Now what I'm going to do here, and I just want you to keep this in mind because we'll come back and talk about this, is I'm going to impact out here on the end of the Jim beam, and this particular mode shape is near a node line. It's not moving much near in the center. So I don't, if I'm going to impact and rove an accelerometer, I want to pick a good point where you know, there's plenty of motion of each of these modes. There's another mode there that, you know, we call that first torsion, maybe first torsion out of phase because the top and bottom plates are different. There's a fundamental mode, that's a torsion mode of the back plate. So we always look for that kind of thing when we test structures. If you take a set of data, I don't care what it is, an airplane wing, a car body, a machine tool, and you don't see something that you can identify as first torsion or first bending, here's some simple bending of the top and bottom, then you probably don't have a good data set. You should see those modes in virtually anything that you analyze. Okay, I'm going to go up here and I'm going to press the impact structure. Now what's come up here is our acquisition window, and it's also popped up a little dialog box. Now I can program MEscope to do all these things and put different prompting messages in the scripting. You can see here that the acquisition window has my time signals up in the top. Here's the impulse from the hammer. You can't really see it's down here at low frequency and then basically 0. And then the 3 impulse responses of the triaxial accelerometer that's mounted on the Jim beam. So I'm going to go ahead and say yes, and we'll just see how this works. I'm going to impact this structure, and let's just hit it, and you can see that it triggered, and I'm going to hit it again, and it triggered again. So I'm doing 2 averages, and it says, do you want to check repeatability? Now, that's assuming that I've already made this reference measurement, and I'm going to compare these 3 FRFs that I've just measured here that are on the bottom with the baseline data that I've already saved. So let's just go ahead and look at that, and we can do this a number of times and come back here. Okay, so here is the data that I just measured in this data block. Over here in this data block is my baseline set of data. And so I've got another little dialog sitting up here telling me the red line is the FRF correlation using SDI. So there is, as a function of frequency, the difference between that measurement I just made and a previous baseline measurement that I had made. So let me go ahead and go back and do that again, and we'll see if we can make a better measurement. Now down here is coherence. And if I scroll through this, well, let me just stop this here and we'll look at what else we measured. There are the coherence values between the three FRFs, and let me see if I can get this display here to look a little better. Format, overlaid by DOF. Okay, so here they are. Here's my three measurements overlaid by DOF, and you can see that in the vicinity of the resonances, the coherence is pretty good. Now again, coherence is a measure of the linear relationship between the hammer, the input, and the accelerometer, the output. You can see obviously the Z direction has very good coherence because that's the vertical, that's how the surface of the gym beam is jumping around. Again, here's the picture of it here. There's the triaxial accelerometer right there, and let me go ahead and hit. I've got to hit this and get it started again. So are you ready? I'm going to say yes, and let me hit it right here. And coherence is 1. Remember, 1 average with coherence is always 1 because the data, the input and the output are lying on the same straight line. Now I hit it again, and you can see the coherence is pretty good this time. Let me put this back, and oh, I have a dialog here. Do you want to check repeatability? Yes. So let's go back and take a look at this. I've got another dialog here. I'm going to dismiss it. And so now you can see I've impacted right at the same point. My repeatability is virtually 1 over all the frequencies. Let me go back and do this now again, and this time I'm going to hit at a completely different point on the structure just to show you what happens here. So I'm hitting way off to a different point, and coherence is pretty good, so at least I hit those two in the same place. But now if I look at the repeatability here, you can see it dropped way down. And again, it's got values between 0 and 1. And here's what I don't like. I don't want to see at a resonant peak, if I'm trying to do an impact test and curve fit this data, I don't want repeatability dropping down in the vicinity of a resonance. There's a very bad measurement because I have impacted in a different place. So you can see that, again, this is a function of the modes and how they're excited from different points on the structure. But this would be a very poor measurement if I'm attempting to impact in the same place. Let's do it one more time. And I'll go back and hit close to where I saved a baseline, and okay, let's check repeatability. There I hit back in the same place again. Now just one more check of this. It says update the baseline. So I'm going to take this data that I just measured and call that my new baseline. Let me do that. And so that's going to transfer that data over and save it away in my baseline data block. And now if I go back and check repeatability between the baseline, and you can now see that the repeatability, the SDI values are all 1 over the whole frequency range, because those 3 FRFs, magnitude and phase, or real and imaginary, think of it as an ODS at each frequency with 6 components in it. The baseline and my current data that I actually saved as the baseline are identical. And so the SDI values are all 1 over the whole frequency range. I have to dismiss this, and you can see that down here they're all the same. So these are, with a little bit of scripting, this is all standard stuff in MEscope. using SDI between two data blocks of data. So this will work with your time records or in this case the frequency records, because this is just processing ODS data at each frequency and putting and displaying a value in the data block of the difference between the ODS at a frequency from a baseline set of data. And now this is zoomed in. They don't look the same here, so let me zoom this one out a little bit, and now you can see there they are. The baseline is over here on the left, and the current that I just measured is on the right. So it's exactly the same set of data when I create a new baseline. Now if I go back here and take some new data, impact again, let's see if I can hit it the same place again and get the same measurement. Okay, coherence is pretty good. Let's look at the repeatability. Not too bad. However, let me dismiss this and see there it dropped out. The repeatability is very poor, but that's where the measurements are, the magnitude is quite a bit less also. So what I'm looking for, just like coherence, I want repeatability to be good in the vicinity of a resonance. If I go over here where it's very low, that's what we call a zero or an anti-node. And again, this is very poor, but remember this is on a log scale, so wherever it's dropped down, and maybe I didn't quite hit at the same point, there's a case there. So that's what the 400 and there's the 494 hertz mode. So I'm a little bit off. Remember we looked at that mode shape, and when I hit it a little bit of a position where I'm off, here's the 492. So that's a torsional mode, and we're very close to a node line for that mode. So that measurement is not quite as good as if I'd have hit, for that particular mode, if I'd have hit a little closer to the same point as my baseline set of data. Okay, so now let's go look at a rotating machine and how we can use this same idea or this same metric to compare what we call an ODSFRF. So it's an operating, it's very similar to a cross spectrum. The only difference is an ODSFRF gives us a true magnitude of the response because its magnitude is the auto spectrum of the accelerometer response versus the cross spectrum, which is the product between the reference and the roving amplitude of response. So I can't really tell how much a machine is moving if I just measure cross spectra. So let's go look at that case. I'm going to shut this down and close the project. No, we won't save it. And let me open this one called route-based repeatability. So this would be, you know, in any kind of a monitoring situation where I want to, you know, take the same set of data over weeks or months, or maybe just for troubleshooting. The machine was running fine when we put it back online. Now it's got some problems. Let's go measure some of its acceleration response, its vibration response, and see whether it's different. Let me move the camera here so you can see that rotor kit a little better. Okay, there it is. Now I'm going to remove the 4-channel analyzer from my computer that I was using for the impact, and I have another 4-channel that I'm going to plug into the computer, and then MEscope will start acquiring data from that 4-channel analyzer, which is hooked up to this rotor kit here. So I'll just switch the rotor kit on. I've already taken a set of data, and maybe you can see the laser. The laser is measuring the RPM. So we've got MEscope set up to take data on this thing. Let me turn that off for a minute. It's a little bit loud. What we've measured in our baseline set of data now is at only 5 points where the blue cubes are located on the model, and we put some springs under it so you can see the animation a little bit better. I'll animate the data here in a second, but the idea of repeatability here is that if you don't, and we have magnets on the the accelerometer here, and also on the various test points on the structure itself. So if you don't orient the triax in the same way as the baseline set of data, you're obviously going to get the wrong results. Let me animate this data. I've already taken a set of data, and so I'm going to go here to my hotkeys and do a comparison. Compare shape. So this is a comparison display. Well, maybe I got to go take some data here first to get this to go. Let's just go start over here. I've got several hotkeys here. This one says next point. Let me push on that. Now what this is doing, this is a capability in MEscope where the acquisition window on the right is actually tied to the model on the left. And I've got what are called measurement sets. So each time I take data on the machine, I'm going to record a measurement set of data from the laser. I'm going to use the laser as my reference and the triax accelerometer as the roving accelerometer. So my laser is just going to measure the speed of the machine, but it'll give me, you can see up here, here's the laser signal coming in, and if I click here and zoom a little bit, you can see those pulses coming from the laser, and then here's the vibration signals from the accelerometer. Down below here is the spectrum. Now you can see this is called an ODSFRF. This is the spectrum of the laser, so you can see the orders, the running speed, 1750 RPM is what it's reading here with the cursor, and then here are the ODSFRFs, basically the auto spectrum of response of the accelerometer for that point. Now there's also phase in there. If we're going to do an animation, we've got to have the phase also. Okay, well, let's go through and try this out here and see each time I click this next button, it's switching the measurement set in the acquisition window, and it's also displaying on the model the roving accelerometer, including its orientation. I have a previous one here, and I can go back. And so I'm going to start here at point number 1. That's where I have the Excel already located, and I'm going to ask it to acquire data. Let's just turn it on here and acquire some data, and I'm going to press the acquire data button, and so it's taking data, and it's asking me here, do you want to acquire data? Let's see if I can make this a little clearer here. So you can see the data coming in here. If I look over in the ACK window, let me see if I can actually, let's stop this. And okay, it's taken 3.9 seconds of data. So I'm set up here for 4,000 samples and a span of 30,000 RPM. Now we're not displaying all that, but you can see the data down here is being displayed up to 6,000 RPM. Let me start that again, and and we'll take some data this time. So we're taking data. You can see it coming in here every 4 seconds. Calculating the ODSFRFs down here. I'm happy with it, so let's go ahead and take some data. So I think it's going to do 2 averages. I didn't show you that, but it's set up to do 2 averages of this data, normal spectrum averaging. And when it's finished, it should come up and, okay, do you want to check repeatability? So let's go ahead and say yes. So what it's going to do here is compare, and there, that red line is the repeatability. So you can see it's very poor compared to my baseline. Now again, I can save this data as a new baseline, and so it says, do you want to add to the ODS? We'll say yes. So here's my ODS data, and I just put 3 components in for 0.1 x, 1 y, and 1 z. But let's go and say new baseline with this data. Now if I go back and check repeatability, let's see what that gives me. There it is. See, this data now is giving me a repeatability of 1 because I saved that as my baseline over here in the waterfall. Let's go back and get some more data and see how repeatable this is on a running machine. I need to put it back here on 1, and now I'm going to acquire some more data. All right, do you want to acquire data? Yeah, let's do that. So this machine is hopping around on the table here, and so we'll just see how repeatable a measurement is where I haven't changed anything. I just went back and made another measurement. Ooh, not good. Now what it's doing, unfortunately, is comparing all of my data in this waterfall. So what I have to do is actually take a whole new set of data by going to each point on the model and creating a new baseline. This baseline has different data in it than I'm measuring here. You can see that. Well, let's zoom in here. Let me say no, and let's just see what we really have here, because again, we're only interested in the running speed. So here's the running speed, and you can see that the SDI value is 1. So the zeros are where I have basically no signal. Here's the first order, and the SDI is right up there at 1. So that's really all I need to worry about. Here's the second order right here, twice the RPM of the machine, and again, SDI has jumped right up there to a value of 95%. Anything over 90% is a very repeatable measurement. Let's go out here to the third order. Here's the third order, and it's jumped up too. And all the other data is, let me zoom this out, you can see it's just not very good. So a little bit different here. We're not going to see it over the whole frequency band. Let me do that again. I'm going to go collect a set of data. So it's only going to show up well where I have peaks in the data. You can see the running speed. There's a second order. Third order showing up a little bit, but hardly in my data at all. Let's go back and take another set of data, and it should be fairly repeatable. I haven't changed anything. I'm just taking more data. You can see it coming in here in the ACK window every 4 seconds, and it should be finished here. Okay, let's check repeatability. And again, I don't care to save it. Let me zoom in here around this peak. So there it is again. There's the first order. It's overlaid. My 3 measurements are overlaid. And so you can see this is a very large peak, but the red line is the the correlation. So we really are just looking at first order ODS here. Let me see if I can compare. I got a little bug in here. I think I'm not being able to compare. Ah, there we go. So here's a comparison of baseline versus the current. Now here's the SDI up here again. Now that is a comparison between the two ODSs. So here I've got 758 RPM, my baseline, and 1777 down here for my current. So a little bit of difference in frequency, but now there's something else going on. You say, well, how can you animate that model with just let me just go here on single animation. Oh, I got to stop. This is another feature of MEscope. We've actually got an FEA model that we're curve fitting mode shapes from. We're fitting that to the experimental data at the five locations. So it gives a nice smooth ODS for this machine at this speed. This is what we would call first order ODS of the machine just from the experimental data. Now in MEscope there's two ways to interpolate between measurement points. One is the geometric. This is a little different. We call this shape expansion, where we're actually using the mode shapes of the base plate and the bearing blocks to animate, to get an animated shape here. So let me go back and show how I can make a bad measurement. I'll click back here on the model, and let me go back to the previous point. Now I'm going to go back here on we'll put it over here and we can look at let me turn this off for a second. Now I'm going to take and just reorient the accelerometer so that X is pointing along the shaft axis direction as opposed to normal to it. And now let's start it up. And so, you know, I'm out in the field and I just don't have this, I'm not paying attention to the model, and I stuck it on the wrong way. And let's start it back up here. And let's take a set of data. And then we'll check the repeatability. Are you ready to acquire data? It looks like it's coming in fine into the acquisition. I'll say yes. So it's going to take at least 8 seconds here, maybe a little processing time involved there too, to finish the measurement. And it says you want to check repeatability. And now let's go zoom in here around the running speed and see what we have. Oh, look at that. See, the red values are way down here, almost to 0. So what it's telling me is that at the running speed, I made the wrong measurement. And here's the second order again, very poor. And the rest of the values are because of the random noise in the measurements. So there is what I wanted to show you. Let's put it back. I'll turn it off and we'll go back and I'll put this back in the right position, and we'll make one more measurement, and then maybe, Mark, we can answer some questions. Okay, let me put this back and we'll start the machine again, and we'll take some data. Okay, I've got data coming in. So there it is. We got the red back up. Maybe not quite as good as we had it the last time, but we got repeatability showing us that we're not 100%, but in the high 90s, maybe 95% at the first order. And the second order, not quite as good. Where are we? 3,400. This one here, well, we didn't quite get that measurement the same. Anyway, that concludes our demo. And Mark, do we have any questions?
Yeah, we do. Yeah, from Dr. Syed Ali. Very informative presentation. Can you please briefly talk about concrete bridges in context of today's lecture with reference to superstructure, girders and slab, and 2, substructure, columns?
Well, I'm not sure what I can add to what he already said. He's describing various pieces of a concrete bridge. We have done bridge testing at Vibrant. We don't do a lot of testing here. We mainly work on the MEscope software, but we have tested bridges. Again, impacting is a good way to test a bridge because the resonances are, the ones we measured were like 0.5 hertz. So you're way down at low frequencies. It's very difficult to excite those frequencies with anything except an impact. So we built our own impactor and we're able to excite the bridge with an impactor, basically a large weight sliding down a pipe and hitting the bridge and impacting it. So again, as I did the test on the Jim beam with or at least described it, impacting at one point and roving the accelerometer is the way you would want to test a bridge. And what we described today would be a good way to measure the repeatability of your data. Now, when you test a large structure, sometimes a hammer isn't sufficient. You know, these impact hammers are, well, you can buy one that is up to maybe 25 pounds, but when you're testing something as large as a bridge, you have to measure what we call a transmissibility, and it's a ratio of a reference or your roving accelerometer to a reference accelerometer. So we've done that. When we tested the bridges, we couldn't measure the force input from the impactor. It was greater than the force range of our force gauges that we had available. So we simply measured transmissibility. But what I showed you today would work equally as well with transmissibility measurements. And then you can do other things. You can measure an ODSFRF, which we did on the rotor kit, where another way to think of the ODSFRF is the transmissibility multiplied by the spectrum of your reference accelerometer. So you get peaks in your data. You can curve fit ODSFRFs in MEscope. You can get mode shapes. Yeah.
Okay, still there? Oh, what happened here? Did we lose you? Still there?
Yeah, I'll check and see if he's still here.
Okay, we lost his audio.
دفعيه عشان ما يقعدش يلف كل شويه ويرجع منك. اديله بسكوت، اديله رضعه، اديله عصير.
Oh, okay, I'm back, Mark.
There we go.
Did you hear any of my answer?
Oh yeah, we heard your answer.
Oh, okay.
Yeah, right at
Any
the
other
end.
questions?
You tailed off right at the end there. No questions. Let me just open this up here to see if we got anybody that has an audio question. I'm gonna go ahead and unmute. Oh boy, looks like we got some background there.
We got some kids in attendance, it sounds like. Okay, well, it sounds like we need to wrap this one up, Mark.
Okay. Yeah, if
All
you
right.
got some questions, let me just leave it with this. We did record this, so you'll get an email link with the recording here. It usually takes about a day or so for us to get the recording saved, and then we'll send out a link so you can go back and view it. And then we'll also be uploading this webinar to the Vibrant Technology YouTube page. So that should be up there in a couple days as well. And if you have any additional questions, by all means, go ahead and send those off to us. You can submit those. Brian, is it webinar@vibranttechnology.com?
Probably support at vibetech.com.
There we go. Let's go ahead and send them to support@vibetech.com. So go ahead and email if you have any additional questions, and we'll get those answered to you.
Next month, we're going to do curve fitting, which we've done before, but that seems to be a popular webinar subject. So in June, we will do some curve fitting, and you're welcome to come back and join us for that one.
Sounds good. We will leave it at that. Thanks, everybody. We will talk to you next month. Goodbye.
Okay.